I'm glad to open the next session of our seminar. Our speaker is Roberto D'Onofrio from the University of Surrey and University of Milano Bicocca. So you see the title. Roberto, you are welcome. Please begin.
Thank you. Hello, everyone, and I'm very pleased to be talking here today, and I would like to thank Professor GDEqfor inviting me to this beautiful seminar. And yeah, so today I'm going to speak about Monge-Ampère geometry and some of its applications to semigeostrophic equations. So let's have a start. So the plan for this talk is as follows. We are going to see some modelistic and physical aspects of these semigeostrophic equations. How do they arise, and what are the main variables involved, and what are the possible routes for their solution. Then we will see something about some basics. We will remind some basics about Monge-Ampère geometry as developed by Lishagin and his collaborators, and I would like to mention among the main contributors, Professor Volodya Rubtsov, which is present here today, and who's one of my main mentors for my PhD program. Then we will see, I will speak about our main results so far obtained in my PhD program, and I'll explain them through some examples. I'll conclude the talk with some outlook and future directions for my research. Okay, so what are these semigeostrophic equations? Well, they are this system of equations, 5 equations, right? And as you can see, they are very similar to the Euler equations of fluid dynamics. Indeed, they are composed by 3 components of the momentum balance. One continuity equation, that is the mass balance equation, of course, and one energy equation. Now, of course, there are several important differences with the Euler equations, because this system is intended to model large-scale atmospheric and oceanic flows. And when I speak about large scale, I really mean that the horizontal length scale is of about...
I'm sorry, G big is my material derivative, total derivative. What is this?
Well, this, of course, is the classical advection operator, this one, plus U.
Yeah. Thanks.
V and W. Okay, so this operator is defined through the physical velocity field. Now, as you can note, here we don't have U, V, and W as usual in the Euler equations, but they are indeed replaced by something else. This something else is called the geostrophic wind. And this special treatment for the acceleration term is, here is missing the acceleration term, as you can see. The special treatment takes account of the fact that this kind of flows are dominated by gravity and the Coriolis force. This is the Coriolis force, okay? And this is gravity which of course only appears in the vertical component of the momentum balance. So the absence of vertical acceleration means that gravity is the only important term, while in the vertical balance, of course, while replacing the velocity field by this geostrophic wind, this amounts to saying that the acceleration term is small if compared with the other contributions in the horizontal balance of momentum. Now, so other important assumptions here are the Boussinesq approximation, which allows us to write the continuity equation as a non-divergence of the velocity field, and the assumption of isentropic flow, which boils down to the transport of this quantity, which is called potential temperature, and it's nothing but a monotone function of entropy. Okay. So, okay, but the most important variables appearing here is the so-called geopotential. Now, as you can see, the geopotential plays very much the same role as the pressure does for classical Euler equations. It enters the momentum balance only through the gradient, its gradient, right? But it doesn't represent actually the pressure. It's something else. And indeed, it represents the gravitational potential, okay? The potential energy per unit mass. Why is this so? Well, the point is that we are allowed to treat the pressure, the real pressure, as one of the independent variables in this formulation, which is precisely this Z. This is nothing but the pressure. Okay. And the reason why we are allowed to consider pressure as an independent variable and the elevation as a dependent variable is that they are monotone functions of each other, thanks to the hydrostatic assumption. So other things worth remarking are that we are considering a domain which represents a piece of atmosphere, which we consider flat, right? The atmosphere is something like this, okay? But we just consider a piece which is 10 to the 3 kilometers long in the horizontal direction. And this allows us to approximate it as flat, okay? And we are going to consider this domain as embedded in R3 with coordinates x, y, and lowercase z. Okay, so then we must mention...
I'm sorry, but you said that Z stands for pressure, or I am mistaken?
Yes, Z represents the pressure, indeed. What is your question? Sorry.
Because here Z is just the spatial in your picture is a spatial variable.
Yes, this is indeed one of the independent variables. Yes, one of the independent variables. We are, in other words, we consider, if we consider Z equal constant, then we are referring to a surface of constant pressure, okay?
Okay.
while points on this surface can have different elevation above the sea level, right?
Mm-hmm.
So in other words,
it is very useful. I'm sorry, just remark. It's very useful when you speak about this isopressure surface for numerical simulation. It is very important ingredient.
yes, it is quite common in geophysical fluid mechanics. It's quite widely used. It's widely used. And in this context, from the mathematical point of view, it allows us to get rid of the density. You don't see any density appearing here, right? And also here. Why this is so? Because this change of variables has absorbed density and made it disappear from the momentum balance, and also allowed us to write the continuity equation in this simple form without any time derivative. Okay, you can see when I write this laser-like drawings on my screen, right? I hope so. You can see this, right?
Yes.
Okay, thank you. Okay, so other important physical quantities are the so-called absolute momentum components. Only the horizontal one are going to actually matter, and they are defined this way. I forgot to mention that this F, which is the Coriolis constant, is the Coriolis parameter, which represents the speed at which our reference system is going to spin around the z-axis. This F is considered constant. Strictly speaking, it's not, but we consider it constant on this length, on this range of 1,000 kilometers. Okay, so I guess that we are done for what concerns the modeling aspects of the model. So we can move on. Now we're going to describe an important observation made by Chenoweth and Sewell about semigeostrophic equations. That is, they were the first ones to ever recognize the presence of a Legendre transformation between four sets of variables of importance for semigeostrophic theory. And their the key point for this observation is as follows. If we define the geopotential this way, we redefine the geopotential, right? This is the physical geopotential, but we modify it in order to get this capital P through the addition of this term. And also we normalize the absolute momentum components and the potential temperature in order to have this quantity, which now has the physical dimensions of a length. Okay, if we do so, then we are able to write down this important relation between capital X, which we are going to call the generalized momenta, and the modified geopotential. Okay, we are able to write this important relation, and this is at the very heart of the Legendre duality as recognized by Chenoweth and Sewell. Let's explain exactly how. Well, it turns out that if we define as dual variables these two sets of variables, we call them sets of dual variables. This is dual to this, right? This is dual to this. Then we are able to write a quartet of Legendre transformations, which is very much similar to the classical one of thermodynamics, right? And this representation means that if we want to find the partial Legendre transform of P, which is the modified geopotential, with respect to the couple of dual variables, lowercase z and capital Z, then we just add these two and set them equal to this, as in this example, right? Then we are able to recover every relation existing between the gradients of T and P, of course, by derivation. Well, so the existence of this Legendre duality has led to many important progress, to some important progress in the analysis of semigeostrophic equations. And is precisely this which allows us to bring Monge-Ampère geometry into play. And let's see why. But before doing so, before talking about geometry, I would like to spend some words about an alternative formulation of semigeostrophic equations, which is called the vorticity stream function formulation. Well, this formulation turns out to be available for many fluid models. Okay, for example, the classical 2D incompressible Euler equations, which can be written this way, right? This is the stream function, vorticity. So we are going to have a Poisson equation relating the stream function to the vorticity. This is a scalar, of course. And a transport equation for the vorticity, where this operator now can be expressed in terms of psi only. And this means that the system is actually closed. Now, boundary conditions are usually tricky when one resort to this kind of formulation. And this is going to make no exception for the semigeostrophic equations. But nonetheless, this allows us to, this is important to recognize that semigeostrophic equations can be indeed written this way. And this is possible if we choose R as our main variable instead of P. Let's just recall what is R. R is the full Legendre transform of P. So it depends only on capital variables. Then if we choose that as our main variable, so that the capital X variables are the independent variables now, we are able to write the semigeostrophic equations as just these two equations, which are very similar to these ones, right? We still have a transport of vorticity. This is a scalar called the potential vorticity. I'm not going to describe it in too much detail now, but it's a sort of vorticity. It's sometimes called the Ertel potential vorticity. And then, in place of the Poisson equation, we have a Monge-Ampère equation. This is a Monge-Ampère equation, right? a key observation is that we are able to write the advection operator in terms of R only. And everything here in blue is something which tries to give you an idea of why this is possible. And of course, a formulation like this would be possible using P as well, and even using S or T. But the equations involved are going to be much more complicated. As you can see here, the advection operator can be written this way, which is not so complicated. There is a gradient of R appearing here, but overall is tractable. If indeed we would like to replace this R by P, then this operator is going to be much more complicated, because it depends, of course, on the velocity field. And in order to express this in terms of P and its derivatives, we will need to invert the equations of momentum balance written this way. So there is an inversion needed if one wants to write this velocity field in terms of P only. Sorry. Right, so using P is not the simplest route, but nonetheless, even if we solve these equations and find R, then in order to get a physical picture, we'll still need to invert the momentum balance equations for the velocity field in order to find what kind of flows, to find out what kind of flows our solution is representing. And we are going to describe this towards the end of the talk, when I'm going to show you, when I'll show you an example of an exact solution. So for now, we can move on. And start talking of geometry. So, so we are going to be interested in symplectic Monge-Ampère equations in 3 dimensions. This is the only class of equations that we will study in this talk. What means symplectic? It means that the equations coefficients don't depend on the value of the dependent variable, in this case R. They can only depend on the independent variables, which for these equations are the capital variables, and the first derivatives of R with respect to these independent variables, that is the gradient of R, okay? And when I speak about equation of coefficients in this case, it really means Q. Q can only depend on independent variables and the gradient of R. In this case, we speak about a symplectic Monge-Ampère equation in 3D. It turns out that the study of this kind of this class of Monge-Ampère equations can be reduced to the study of phase space, that is the cotangent bundle to the space of independent variables, equipped with a so-called Monge-Ampère structure. A Monge-Ampère structure is made of a couple of differential forms, of which we have, it comprises a symplectic form, okay, and we take the standard one. And a Monge-Ampère form is what we call a Monge-Ampère form. Okay. This Monge-Ampère form actually represents our Monge-Ampère equation in this geometrical setting. Now, these two forms satisfy this condition. Why? Because it turns out that there are many possible choices of this omega to represent our equation, but only one which satisfies this. That is this choice. This is the only choice which is Q orthogonal to capital omega. Now, well, so we are studying the phase space endowed with a Monge-Ampère structure. And the next step is to define a solution. What is a solution of a Monge-Ampère structure? Well, the definition is as follows. A solution is a Lagrangian submanifold of the phase space, that is a three-dimensional submanifold in this case, which satisfies this equation and which also satisfies this one. This is going to be the actual requirement for L to be a solution to our Monge-Ampère equation. And I want to point out that if there exists some function p of lowercase x, this is lowercase x, right? If there is some function p of lowercase x such that L is the graph of its gradient, okay, the gradient is going to be, as we have seen, a map from this space to this space, right? This holds thanks to this relation found by Chenoweth and Sewell. So if there exists some function p such that L can be represented as the graph of the gradient, then this equation is going to boil down to just a classical Monge-Ampère equation, right? And this is only possible if our Lagrangian manifold is in graphical form, that is the graph of a function. So this takes us to this important distinction. We speak about classical solutions. Classical solutions as those which can be projected nicely to the physical base space. And this is equivalent to say that there exists a function such that L is the gradient of that function, is the graph of the gradient of that function, right? This is very much the same thing. While we speak about generalized solutions, which are Lagrangian manifolds which cannot be projected everywhere nicely onto the base manifold, right? There are at least, there can be singular sets. The singular sets cannot be projected nicely to the base manifold, and their projection gives what we call the caustics. Okay, so for example, this solution here cannot be represented as the graph of a gradient of a function, right? This is not possible. It can be done locally here, or maybe here, but we can't find one function which is able to describe this globally. Nonetheless, we are able to describe every generalized solution, even if we look at points close to the singular set, by means of a single function, a generating function, right? Because these are Lagrangian submanifolds, and they are locally described by generating functions. And it turns out that the dual potentials recognized by Chenoweth and Sewell can be indeed interpreted as generating functions in this context. Generating functions which locally describe a generalized solution. Now, if we pick one of them, for example, T, let's assume that this piece of solution is locally described by this generating function. Then this condition, the condition for it to be a solution, boils down to some sort of Monge-Ampère equation. Okay, this is the Monge-Ampère equation, which is satisfied by the generating function T, which is different. It looks different from the one which P satisfies or R satisfies, but it's equivalent in a precise sense. In which sense? The equivalence of Monge-Ampère equations is defined as the two Monge-Ampère equations are equivalent if their generalized solutions set coincide, right? This turns out to be exactly what we are doing. We're looking at a Monge-Ampère equation equivalent to the one I showed you before. Now, so this concludes the introductory remarks about the geometry of Monge-Ampère equations. And we're ready to introduce pseudo-Riemannian geometry into this context. So it turns out that the phase space can be equipped with a metric which is compatible with the Monge-Ampère structure. This metric has been introduced in the first place by Lyshagin and Rubtsov, and this is why I'm going to call it the Lyshagin-Rubtsov metric. And later, Bamos recognized that this metric is indeed part of a generalized Calabi-Yau structure. And this is the precise sense in which G omega is compatible with our Monge-Ampère structure. But I'm not going to describe what Calabi-Yau structures are or generalized Calabi-Yau structures are. I just want to point out that for semigeostrophic equations, G omega is just this, okay? We can compute it through a simple formula, and it boils down to just this for semigeostrophic equations. What is this? This is just this thing, right? If we want to represent it in a matrix form. This is an identity 3 by 3 and so on. Now, the main question for my PhD project is, what is the meaning of this G omega for SG equation, for semigeostrophic equations? And in this next slide, I'm going to show you which are our results obtained so far in this direction. Well, first of all, the signature of the pullback metric, we're going to consider the pullback metric on solutions. Okay, the signature of this object is related in a very specific way to the symbol type of the Monge-Ampère equation, it turns out that the signature of H is 1, 2 on hyperbolic branches of a multi-valued solution, of a generalized solution, is 3, 0 on elliptic branches, that is, only positive eigenvalues, one positive, and 2 negative eigenvalues. And last, H omega is degenerate on parabolic points. Second point, parabolic points of every generalized solutions are always singular. And in order to visualize these statements so far, the statements I've described so far, we can have in mind this drawing. This is a typical situation in which we have a generalized solution L, and the symbol type of the equation can change from elliptic from hyperbolic to elliptic exactly when we move across a singularity. Okay, singularities are parabolic points, and there is this switch of type as we move across it. Okay, and last, we are able to construct characteristic surfaces, for example, in this form, as solutions to the econal equation, where the econal itself is nothing but the Lyshagin groups of metric on L. Okay. So instead of giving a proof for the statements, I would like to show you how they look like in a specific example, and then we can describe how these statements are justified. So we can consider this example, this simple example, right? This is a simple solution to the Monge-Ampère equation I've introduced above, this one. Okay, this is the Monge-Ampère equation satisfied by a generating function t. There is this q here. We set it equal to 1, and then a simple solution to this equation is just this one. Okay. Now, why I chose this t to represent locally L? Because it's simple in these coordinates to describe a Lagrangian fold, a Lagrangian singularity, a Lagrangian fold. Okay, which means that our Lagrangian submanifold is going to look like this. There is just one fold somewhere, or at least locally, as long as we can use T as a description for L. Okay, and this is the term which introduces this fold, this cubic term. Also note that there is a trivial dependence on y. Why do I say trivial? Because this is just a quadratic function, and quadratic functions are going to be not very important when we carry out a Legendre transformation, as we shall see. And the presence of this trivial dependence on y is what is going to make the actual fluid flow arising from this generating function actually 2D, two-dimensional flow. Okay, it's not going to depend on y. But let's see step by step how to get there. First of all, we can recover the expression of the Lagrangian submanifold that degenerates through this set of equations. Okay, these are just classical equations, which allows us to describe a Lagrangian submanifold through a generating function depending on just these three variables. Then we are able to compute the pullback metric on this particular solution, which looks like this, and also the singular locus for the projection mapping. Okay, the projection mapping. Why I forgot to mention why I'm so interested in this projection instead of this one. Okay, why do I speak only of this projection and I look for singular points of this projection only? Well, because this is the only projection that allows us to recover physical information from this geometrical reasoning, right? We are not going to obtain any physically meaningful information by projecting L on the momentum space. So, okay, and so we can observe now that the Lyshagin roots of metric on L is quite easily to analyze now. Its eigenvalues are just these ones. And from this, we see that the problem is hyperbolic over here. That is for Z bigger than 0, capital Z, and elliptic over here for Z less than 0. While the singular locus is just the plane Z equals 0. When I say plane, I of course refer to this local description of L. Okay, so let's have a closer look to this solution. If we zoom in close to this singular locus, we will see something like this. This is a capital Z, lowercase x, lowercase y. These are coordinates on L, on the Lagrangian submanifold, sorry. And the singular locus, the sigma L, is just this red plane here. Now, if we project it to the physical space, we get this picture. This is a lowercase z, of course. And there is another key observation here. There is no physical points to the right of this singular point, right? But points here are not related to any physical point for the fluid flow. The fluid flow can occur only here. Okay, and this region where the flow is going to be two-valued, of course, because we have two branches of L, is going to correspond to the region below this caustics. Okay, so the region below this caustics is what we may identify as the fluid domain. Well, so with this picture in mind, we can now speak of characteristic surfaces I would like to remind that the problem is hyperbolic over here. That is for z bigger than 0. And when the problem is hyperbolic, we are able to solve the econal equation, which in this case is written like this. And its solution can be written this way, which represent this cusped surface intersecting the singular locus along a cusp, a semi-cubical cusp, right? And this is an important behavior, which is the classical behavior of characteristics close to the parabolic set, because I want to remind that the singular locus is always parabolic. This is consistent with that. And another observation is that this characteristic surface is foliated by light-like geodesics of the Lishagin groups of metric. And this is a way to, it's an important, not so important, right? But just an observation which allows us to bring some meaning to the Lishagin groups of metric in this context. That is, light-like geodesics are foliate characteristic surfaces. Well, now we are ready to recover physical information from this generating function. How do we do that? Well, now we have to use the momentum balance equations, which are these two, plus the energy equation to find the velocity field. We couple these equations with the equations defining L, so we can consider capital X, capital Y, and lowercase z as known functions of X, Y, and capital Z, which are coordinates on L. So we can write these three equations in extended form this way. And our unknowns are going to be these ones, these blue variables, X dot, Y dot, and capital Z dot, which represent the lifted velocity field on L, this blue arrow. We need, as a second step, to recover physical velocity field, to project this velocity field to the base manifold of the cotangent bundle. So this is going to be a linear system of algebraic equations. We can solve it. And in this simple case, we are able to write explicitly the velocity field in the physical space. That is the yellow arrow over here. It turns out that there are only one non-zero component of it. And the only one non-zero component is actually the y component. This is an interesting observation because as I remember, there was this trivial dependence on y in the generating function t. It turns out that the only non-zero component in this case is exactly y component. Now, what we can see from this picture is that the velocity field is always tangent to the caustics. this is consistent with the intuition that this representation may suggest, right? Because if I have a velocity vector over here in the singular point, then it would have zero projection in this schematic view, right? And this means that the velocity field, the physical velocity field, is tangent to the caustics. Now this turns out to be a particular case to a more general statement, which is the following: caustics are transported by the velocity field. Now, in our example, t didn't depend on time, right? There is no dependence on time in this example. And that's why the velocity field is just parallel to the caustics. But if we introduce some dependence on time, we can do that. It's not so difficult to introduce it. Then we can prove, it's easy to see, that caustics are transported by the velocity field. And this slide tries to give proof of this statement. And the proof is as follows. If we just consider the singular locus, okay, as parameterized by some function sigma, and for our example, sigma is just this, because x and y can be taken as local coordinates on sigma L for that example. But in general, we're going to call R and S our parameters. Then we can compute the difference between the surface velocity and the lifted fluid velocity in L. Okay, we are in L now. We want to compute the difference between these two velocities. Now, this is not going to be in general tangent to the caustics, because caustics are not necessarily transported in L. Sorry, the singular locus. This is not the caustics. Singular locus. Singular locus is not necessarily transported in L. But if we now project it to the physical space, we project this difference, right, to the physical space, and then compute it normal component to the caustics, this is going to be 0, because we can write this whole operation as this one, and the determinant of this is 0 by assumption, because we are restricting our attention to sigma L, where this thing is singular. And this is a matrix where the columns are these ones. Okay, these are matrix specified by its columns. Okay, so what does it mean, this observation? Why it's so important that caustics are transported by the velocity field? From the physical point of view, it's important because this means that we, in stationary conditions, we can understand caustics as the boundary of the fluid domain. So boundaries can be described by projecting some generalized solution to the base manifold. And for time-dependent velocity solutions, then caustics can represent surfaces of discontinuity propagating in the fluid, which are transported by the fluid flow. And an important example of this are atmospheric fronts. Atmospheric fronts are modeled as surfaces where the flow field suffer from a jump discontinuity, and they are transported by the fluid flow. I forgot to mention a key fact here. There is a plus minus. which I forgot here. Why didn't I put plus minus? Because there is a preferential choice here, a preferred choice for restore physical single valuedness of the solution, which is to take the only branch of L which corresponds to a convex, the gradient of a convex geopotential, right? What I mean is that each of the two branches of this solution can be described independently as the gradient of some P, right? There is one P for this one and one P for this one. But only this one is going to correspond to a convex P. And this principle is called allows us to select a physical relevant branch from a multivalued solution. And this principle is called the convexity principle and was introduced by Callan, Norbury, and Purser. I forgot to add a citation of this here. Okay, so this is all about this example. Now we are ready to discuss very quickly, I guess, the consistency of the main results. Okay, so how to prove that statements. So we need to start from a definition, which was given by Harvey and Lawson. The symbol type of a nonlinear partial differential equation at some solution is the type of its linearization about the solution. We will need this linearization definition in order to define the symbol type of a Monge-Ampère equation at a solution. Of course, this definition works only for classical solutions, because when we have a multivalued solution, we can't carry out any linearization anymore. But we can linearize the equation satisfied by the generating function in presence of singular points, right? We can just take the linearization of that to define the symbol type of the equation along this solution. We can do it locally through generating functions. If we do so, for example, if we choose t as generating function, and let's remember that it satisfies this equation, then we can linearize this equation around some solution t by adding a small perturbation delta t and retaining only linear terms in it. Then we are able to write the linearization as a linear PDE for delta t with matrix A, with coefficient matrix A. This is the coefficient matrix for the linear equation satisfied by delta t. Okay. We are also able to compute the Lishagan groups of metric for a solution generated by t, which looks like this, and a simple comparison brings this formula. Now, this formula tells us everything, because if A, for example, if we have A with signature 3, 0 or 0, 3, then we call the problem elliptic whenever this occurs. And thanks to this relation, here ADJ represents the adjugate matrix, okay, the cofactor matrix. Then thanks to this relation, if A has these eigenvalues or these ones, then H is going to have these eigenvalues, okay? While if A has one positive and two negative eigenvalues, or vice versa, then H is going to have one positive and two negative eigenvalues. This is very simple, right? And of course, this tells us that if the problem is parabolic, that is A is degenerate, then also H will be degenerate. Now, how to link all this with singularities? Very simple. We rely on a local description again by means of T and write the projection mapping from L to R3, its derivative, which is singular along this set, right? Now, this condition we can see here, when this is 0, H is singular, but also A is singular, because the determinant of this one is going to be equal to this, thanks to the fact that T satisfies the Monge-Ampère equation. Okay? This is the determinant of A if we multiply it by Q. So this shows that for solution represented by T, of course, the Sieg-Jean property of H holds, and also the relation with singularities. Singularities are always parabolic. Now we can, of course, carry out this same calculations for every other generating function, like S, R, of course, P, and everything else in between. There are in total 8 possible generating functions, but each of them brings the same result. So yes, we are going to just discuss T. And okay, there is even an extra slide about the characteristics, which I don't want to discuss now. If someone is interested, we can, because we are running out of time, I guess. Right? So I'd just like to mention my some
Roberto, you have time, so don't be in a hurry.
Okay.
No hush.
Okay. Okay, so let's give just a quick justification, a formal justification for the econal equation in this context. We can just reason as follows. We can identify if we have a parabolic branch. Now, suppose we have a solution where there is a hyperbolic branch. Well, this hyperbolic branch is regular, okay, according to the former discussion, and can be represented as the graph of some the graph of the gradient of some p. Now we are able to use this very relation here to express H omega in terms of A and the determinant of A. We can do that because because A is non-singular on hyperbolic branches, right? So we can write H omega this way. This is nothing but, of course, this is the same as writing adjugate of A. And we can now apply a definition which holds for classical characteristic surfaces. I mean, for classical, for linear partial differential equations. Characteristic surfaces are defined as surfaces which satisfy this equation, which in our geometrical setting boils down to require this one. Here, I got rid of the determinant because it's non-zero as long as we are in a hyperbolic region. And this equation can be solved by classical methods of geometrical optics, which if you want, I can show you this computation, but are very classical ones. So in order to solve this equation, one introduces an Hamiltonian function, find bicharacteristics, and project bicharacteristics to the base manifold, which is going to, maybe it's better if I explain this with some detail, right? If you're interested, because this is going to be very classical computation. Otherwise, since we have some time,
it's not necessary. I think this is more or less clear.
Okay. Since we have still some time, I can show you another example, which is somewhat more complicated than what I've shown you yet, which is this one. Let me de-share my screen and share it again. This is another example which shows, nonetheless, more or less the same properties. So back to meeting. Okay, share screen. I was panicking for a while because I thought I was out of the meeting. So okay, now you should be able to see my screen again. So there is the next step in complexity is the cusp singularity, right?
Can you make a full screen?
Yes. Okay, so this is next step in complexity if we want to study singularities. This is the cusp. This is a generating function for the cusp singularity. So what is the cusp? Of course, everyone knows it, but it is basically made of two folds which at some point meet to an even more singular point, which is called the pleat point or the cusp point. So this is going to be the part which represents this this cusp, while these terms are just needed to make T a solution of its Monge-Ampère equation. The Lagrangian manifold is recovered this way, and its projection to the physical space reads like this. We can see from this that the singular locus is going to be a parabolic cylinder this time. This is the figure. This is the figure. There is a y-axis perpendicular to the sheet. And this is the singular locus. all this represents a piece of L, of course. And this is going to be the singular locus, this dashed line. Now, we are able to, okay, and this is, of course, a three-dimensional view of it. Well, this is the caustics. Once we project this into the physical space, we are able to draw this this surface, and the surface is singular. Is singular, has a cusp along all this line, which is a peculiar feature of the A3 singularity, according to the classification by Arnold. Okay, this is a typical feature of the cusp singularity. So, yeah, so that's the caustics, singular locus. Not going to discuss this for the moment. We are able to compute, as always, the Lechagan groups of metric on L, which now looks slightly more complicated, but only slightly. We're able to compute explicitly the eigenvalues, of course. And from these eigenvalues, we see that the signature of the metric is going to be 3, 0 in the green region and 1, 2 in the red region. So the red region is the hyperbolic region, while the green region is the elliptic one. Okay, and now we can look for the characteristic surfaces, of course, in the hyperbolic region, solving the econal equation in this setting. And here there is a sketch for the computations involved. We have to define an Hamiltonian. This is the most effective way to do that, to define an Hamiltonian. This Hamiltonian is a function on the cotangent bundle to L, okay? This is, if this square represents L, we need another square to represent the cotangent bundle to it. And this function, this H, is going to be a function on that. Then we can write the canonical equations like this, which are subject to the initial condition to be light-like. This is somewhat less clear than everything else, I admit it, because I'm rushing a bit now. But in the end, we are able to write the characteristic surfaces in parametric form this way. And one typical characteristic surface is depicted here. This is the singular locus in L. This is capital Z. So we are in L, and this is a characteristic surface. And as before, it meets the parabolic locus along a semi-cubical cusp. Okay, this time we are not so lucky when it comes to recovering the physical flow field, because this example is more complicated. But we are nonetheless able to get it in parametric form. In parametric form. So U, V, and W, that is the physical velocity field, now reads like this. There is this parametric dependence on capital Z, which must be eliminated by solving this cubic. So I wasn't able to draw a picture of this field because of this parametric dependence on Z. Yes, and that's it for this example. I guess I've got no more to to speak about for today. Just maybe the some outlook and conclusions. So let me share the screen again. Outlook and future directions. We are going to look at the curvature of G omega and its pullback on solutions. It's going to be the next step in my project. There is another important, so in order to answer questions like what does curvature represents in physical terms in this context, has it some physical properties? And the second question is, does dynamics induce a geometric flow on G omega or H omega? And how does this geometric flow relates to the onset of singularities? And the last question, which I'm dealing with currently, is the connection with optimum transport theory. Because it turns out that semigeostrophic equations can be formulated as a transport problem, and the Lyshagin groups of metric plays a key role in there. Yes, this is a matter for another talk, I guess. And yes, so this is all for my presentation.
Okay, Roberto, thanks a lot for a very interesting and nicely presented talk. Giovanni and Volodya, do you want to add something or comment?
Sorry. Maybe Giovanni wants to say something. Oh,
Hi, Giovanni.
Yes. Yes. I think that the connection. So the third point of the outlook is something which is starting now. So is really in the preliminary form. But in particular, I want to stress that these 3 points are ordered in some sense results that we already obtained on this subject, and in particular, so some natural question is the following. So it's a comment, it's not a question, maybe. There is this really interesting structure, which is this metric. And the natural question is, if I have this fluid motion, and obviously, and I can construct explicitly this fluid motion, this is something that I want to stress. It's really important that this method with the Lyshagin groups of metric is something which is explicitly. So one can explicitly find solution of the semigeostrophic equations. So this fluid motion induces a motion on the metric, so a deformation on the metric, which is in principle only parametrical. An absolutely natural question, I think, is so it's possible to give some purely geometrical interpretation to this motion. So this is the following step to the understanding the geometrization of this set of equations. So if it's possible, and this is obviously the answer of the points 1 and 2. So this is my comment on this last slide.
Thank you. Any more comments, questions, remarks?
well, I just add a few words to what Giovanni said. It's indeed when we introduced with Valentin this tensor, the main object was, of course, just to give a tool to classify three-dimensional Monge-Ampère equations similarly to what we did in 2 dimensions. And we wrote this quadratic form and studied the signature and the corresponding geometry, which also geometry was studied by my French PhD student, Bertrand Banos. And what we
I'm sorry. And when we started with Valia, this Monge-Ampère stuff and this metric, was it in 2 dimensions or in 3 dimensions?
Yes, the initial motivation was, of course, from the classical Sophus-Lie question, which was 2-dimensional.
Mhm.
And the answer was very clear in the case of non-degenerate constant coefficient Monge-Ampère equations, that Sophus-Lie was almost right, and all 2-dimensional Monge-Ampère equations can be quasi-linearized. He supposed that it is possible to linearize, but it was only quasi-linearization under, of course, under analyticity conditions. The question for smooth case is still, for me at least, unclear. Valentin thinks that it is clear, but I don't share this because I don't understand the smooth situation. But in an analytic situation, the answer was positive. If you go to so-called generalized Monge-Ampère equation, in fact, generalization was only because Sophus-Lie never considered, and Monge and Ampère never considered 3-dimensional, 4-dimensional, and so on Hessian minors relations. So in this case, of course, the answer was negative, and we proved it in 1983. We proved it for n equal to 3 that this, and to prove it, we need to construct some invariant, and this invariant was absolutely beautiful quadratic form. And this quadratic form, what Roberto generously called Lichagin-Rubtsov metric. What we didn't do, we never considered this object like a metric on Lagrangian submanifolds, and it was a novelty and main, I would say. I asked Valentin, by the way, when we started to discuss with Giovanni, Ian, and Roberto this stuff. I asked Valentin, do you know something about how this metric behaves on Lagrangian submanifold? He said, no, I don't. And I said, me too. And why? And he said, because it's shame to us. It's really shame. It was really shame to us not to study. So we just try to improve the situation. Thanks, Roberto. His input is incredibly rich.
Okay, thanks. More questions, more remarks? Well, then, thank you very much. I wish you a goodbye, and let's meet hopefully next Wednesday. Everyone is invited. Goodbye. Thank you, Roberto.
Thank you. Thank you.
Thank you,
Bye-bye.
Roberto. Bye. See you tomorrow.
See you.